Welcome to the first in a series of videos on the study of thermodynamics as it applies to chemistry. Thermodynamics, literally as the name implies, is the study of heat, symbolized by the letter Q, plus work, symbolized by the letter W. It's a way to quantify what's known from everyday experience. For instance, energy flows from hot to cold. If you drop a ball, it will go down. These are thermodynamic principles that actually are well known but have to be quantified. In other words, thermodynamics is a theory about how the universe works. It's a way to quantify what we already know. And in forming this theory, it's based on well-defined parameters which must be understood. First of all, any system has boundaries attached to it, and those boundaries are well defined. This leads us to understand what the benefits or the limitations of the theory are. The very first definition that one goes to, definition of the system. Very simply and very grandly, the system is the part of the universe that one is studying. Systems can be defined in 4 different ways. The simplest system is what's known as an open system. In an open system, mass can enter or leave, and heat can also enter or leave. An example of an open system would simply be a pot on a stove, where mass can enter, you can fill the pot with water. Heat can enter. You can turn on the stove. As the water heats up, the water is escaping as steam, and the steam is also hot, so heat is also escaping. This is an open system where everything can get in or out. Alternately, a system also could be considered closed. In a closed system, mass is contained. Mass may not enter or leave. However, heat is free to move in or out of the system. A common example of a closed system would be a pressure cooker. In a pressure cooker, you can add mass, the example is water, and you can add heat. However, even though the pressure cooker gets hot and heat is escaping, mass cannot escape, so the water very simply stays in the pressure cooker and increases the temperature, and increases the pressure rather. So a closed system, the mass can't get in or out, but the heat can get in or out. Type of system is a new word for the day. It's called adiabatic. An adiabatic system is open to mass, meaning mass can enter or leave the system, but it does not allow heat to enter or leave. Surprisingly enough, these are very common in everyday life. Things like a thermos or a coffee cup are adiabatic containers. An old-fashioned styrofoam coffee cup was open to mass entering or leaving. You could fill the cup up with coffee, and you can drink the coffee can go out. However, what made the coffee cup special is that it kept your coffee hot. The heat remained inside the cup, and the cup itself stayed cold to the touch. This is an example of an adiabatic system. Is essentially purely theoretical. An isolated system exists if nothing can get in or out. Mass may not enter or leave. Heat may not enter or leave. While these can be approximated in the laboratory, in reality, the only truly isolated system is the universe. By definition, a universe is a system which contains everything and which nothing can get in or out of. So, 4 different types of systems where the system is what you are looking at. The second thing to understand in thermodynamics is perspective. In other words, where exactly are you looking? In thermodynamics, the sign plus or minus denotes direction of movement. It's important to realize that you are essentially sitting inside the experiments thermodynamically. Observations are made from the point of view of being inside the system. So, if you get a result of a positive change, that means heat or work is being added to the system. An example of this would be a common spring. If one compresses the spring, you are adding ability to that spring to do work. Essentially, a potential energy is being added to the spring, like winding a watch, and over time, that spring can be allowed to do work in the future. A negative change means work or heat are being removed from the system. So with the same spring, as with winding up a watch, once you release the spring, it will start to expand. It is performing work, but it is also changing the potential energy to kinetic energy. So as the spring expands, it has less ability to do additional work. So in the system, positive means you're adding heat or work. Negative means you're removing heat or the ability to do work. Heat and work, what do they mean? Starting with work. Work was defined thermodynamically at the point of the Industrial Revolution. It's defined as the result of expanding a perfect gas and moving a frictionless cylinder against a constant external pressure. A very precise and technical definition, essentially, you would have a system with a piston in it, pushing against the atmosphere. As you expand a gas, when that cylinder is moving, it's actually pushing the external atmosphere. Mathematically, that's expressed as dW, where d signifies the change, in work in this case, is equal to minus the external pressure times the change in volume. Once again, the negative sign indicates direction. By expanding, the gas in the cylinder is losing the ability to produce further work. So looking at the definition of work with an example. I do something simple like blow up a balloon. How hard is it to blow up a balloon? If I want to blow up a 100 milliliter balloon to a final volume of 1.5 liters, how much work am I doing since I am pushing that balloon against the external pressure of 1 atmosphere? The definition of work does not change. So in this case, dW is minus P external times delta V, where always delta is final minus initial. So simply filling in the blanks, I have an external pressure of 1 atmosphere. Being careful about units, if I have a final volume of 1.5 liters, my initial volume of 100 milliliters also has to be converted into 0.1 liters. So the amount of work that I do is minus 1.4, and again, watching the units, liter atmospheres. This is odd because, again, work is the expending of energy, and energy is measured in joules. How you get liter atmospheres to represent energy goes back to a previous series of videos on gases, specifically the gas constant. If you recall, from the ideal gas law, the gas constant had a value of 0.0821 liters times atmospheres per mole degree Kelvin. However, why the gas constant is universal and what it actually represented was the potential energy of 1 mole of independent particles. So it also has a value in joules of 8.314 joules per mole degree Kelvin. So in this work, to convert the answer into the proper unit of joules, the amount of work I did of 1.4 liter atmospheres, I would simply multiply this by the ratio of R over R. Units canceling, R divided by R still equals 1, but the liters cancel, atmospheres cancel, moles and Kelvin cancel, and the only thing that's left is joules. So by blowing up this balloon, I have expended 141.8 joules of energy. X means heat and work. In this video, we went into work in some detail for the simple reason to complete the study of work, since it generally does not have much of an impact in chemistry. Heat flow, however, needs more attention. Start with the basic fact that everybody knows. Heat is proportional to temperature, but it's not exactly the same thing. You add heat to something on the stove to raise the temperature. When you put something in the refrigerator, you're removing heat, so the temperature lowers. However, just in everyday common events, you use heat to cook, for example. So, if I want to cook a bird, how much heat would I need? Well, what kind of a bird are you talking about? Are you cooking a chicken or a turkey? I believe everybody realizes that it takes a turkey longer to cook than a chicken, for the simple reason, even though you are cooking both birds, the turkey weighs more. So you have to add more heat to the turkey in order to raise the temperature. Therefore, heat is also proportional to mass. Also, when one cooks in metal pots and pans. Why does one choose metal to cook things faster? Again, a common scenario. You're in the park on a sunny day. There's a wooden bench and a metal bench. You are not going to sit on the wooden bench. You're going to sit on the wooden bench because the metal gets hot. Why does the metal get hot faster than the wood? Has to do with an intrinsic property known as C, the specific heat of the material. Again, this is an intrinsic property of any given material. The units are joules per gram degree Celsius. In other words, the specific heat is how much energy it takes to raise 1 gram of a material by 1 degree C. Wood has a very high specific heat. It takes a long time to absorb heat. Metal has a low specific heat, which is why the bench in the park heats up faster than the wooden bench, but it's also why you use metal pots and pans to cook, because most of the heat is going into the food as opposed to heating the pan. So, putting all of these together, the definition of heat flow thermodynamically is the change in heat, dQ, is the mass of the thing being heated times the specific heat of that object times the change in temperature. As mentioned, heat flow and energy flow is central to the studying and understanding of chemical reactions. Therefore, we will go into detail on heat flow in the following video to give it its own time, which is linked in the description below. Thank you very much for listening, and I hope you found this useful.